Good morning. This time I'm just going to continue with elementary chemistry, school chemistry if you like. It'll be good for early college too, okay? Because there's nothing more you can do with this stuff. Alright, so I recommend that you guys go back and look at some other chemistry related things that I did. I did the mole, twice I think. I did some thermodynamics of ideal gases, and I did scientific notation, and I did density. You should look at density. This is more chemistry specific. Now yesterday I started naming chemical compounds and writing chemical formulae. Now that's very important if you want to depict chemical reactions and what goes on in them. Now there were two equations which I wrote down which had an inconsistency in them, and it's there kind of on purpose. Today we'll solve that problem. We'll look at the equations and see what is meant by that inconsistency, and we'll learn how to do something else with equations. Now I tacitly assumed that you would pick up on the fact that chemical reactions can be represented by equations. You can have equations in words, in formula, and in structural formula actually if you're doing organic chemistry. So this is more of this stuff. Now, there are many different kinds of chemical reactions, but easy ones to study involve salts. Now what's a salt? Salt is an ionic compound between a metal and non-metals, okay? It could be one metal and one or more non-metals. Now a common one would be, let's say, potassium iodide. Potassium iodide, potassium, K, has one electron in the outside shell. I put a 1 in just to be, let you know that that's a 1 electron in the outside shell. And iodine is a halogen. Fluorine, chlorine, bromine, iodine, and acetylene are halogens. Fluorine being at the top, chlorine next, bromine. Bromine is a poisonous liquid. Iodine is a solid. Has 7 spaces. 7 spaces means it would like 1 electron to be complete, right? So what happens here is that the potassium has a nucleus, 2, 4, 6. It has 7 spaces and 1 electron in the outside shell. Iodine has 7 outside electrons in 1 space, so the potassium can give this electron completely over to the sodium, in which case it becomes ionized. That means it has an imbalance in its charge. You take away 1 electron and you've got an extra proton in there. It becomes positively charged. A net charge of +1 is on the potassium atom. Iodine picks up an electron, it gets a net charge of -1. So they cling together. Positive and negative charges attract, and it makes an ionic bond. Now, H2O, CO2, NH3, and all those other covalent compounds, the compounds made up only of nonmetals, they're covalent bonds. Covalence means the electrons are fully shared and they move around whatever partner nuclei are involved in the reaction. For example, if it's carbon monoxide, CO, the carbon atom and the oxygen atom share the electrons, the valence electrons. They move around between each other. But in the ionic bond, in the case of salts, the electrons are completely given over. Now another compound would be potassium nitrate. Right? Because in this case here, you're not taking a single element, you're taking the nitrate radical. It behaves as a unit. I listed some of them yesterday. The nitrate, maybe I didn't list this one. Anyway, we'll look at this compound in a minute as an example. Potassium nitrate is its name. Potassium gives over one electron to the nitrate radical and hangs onto it. This is just a single non-metal, but this is the radical N stuck with O3, potassium nitrate. So now let's look at our equations. This is an example of a acid and metal gives a salt and hydrogen. So a way to prepare hydrogen in the laboratory is to throw acid on a metal. Now to do that in a laboratory, you wouldn't throw it on sodium because that would be a very dangerous reaction. You throw it on a different metal such as zinc or copper. And then you would get hydrogen gas given off and you collect it somehow. So here's the reaction. Now, yesterday I wrote down actual equations depicting a reaction. We could depict a reaction, first of all, in words. Hydrochloric acid, throw it onto sodium. We get a bubbling and a fizzing. Table salt is formed and hydrogen gas gets given off up into space, right? Now in equations that means we can write HCl as the formula for hydrochloric acid, Na, the symbol for sodium, NaCl because the Na kicks out the hydrogen and the hydrogen goes in and escapes. It just goes away. So we get the salt and hydrogen, okay? Now let's deal with this. And let's show the inconsistency in this equation that's going to show up. This equation is all very fine, but we would like to have an equation that tracks all the atoms. When you get hydrogen in the room, floating around in the air, or in a balloon or whatever, it doesn't exist as a single atom, a H. There are not single atoms going around there. There are two things. Hydrogen atoms cling together. We get a hydrogen molecule. Hydrogen gas consists of a collection of H2 molecules. So we have to put that in. Now the equation is disturbed. What's wrong with it? It's not balanced. Let's see why. We have one hydrogen here, but we have two over here. We have one chlorine here, that's fine. One sodium here, that's fine. This one is the only problem, okay? All right, the general way to solve this problem is this. Put a bracket around these guys here. Don't put a bracket around this, and just multiply by 2. Now let's remove the bracket. That means this. We take 2 molecules of hydrochloric acid and 2 atoms of sodium. They together make 2 compounds, 2, let's say, molecules if you like. These are not molecules, but 2 structures with NaCl in them and 1 with H2. Let's check for all the atoms now. 2 NaCl. That really refers to twice this whole guy here. 2 HCl really refers to twice this whole guy here. We could use the brackets. So we have 2 hydrogens here and 2 hydrogens here. 2 chlorines here, 2 chlorines here, 2 sodiums here and 2 sodiums here. So it's balanced. So that equation is now balanced. We had another equation on the board yesterday which was also not balanced, and it was a different kind of reaction. Let's deal with that one. So we see how to do this. You just play around with it. Now there are techniques to do complicated ones, but we're only going to do simple ones to start off with. So get your heads around that while I change it. The next reaction also involves an acid. So we'll take an acid plus a base instead. Now, a base is denoted by something mysterious plus an OH. An acid is denoted by a H plus something else mysterious. For example, HCl, H2SO4, NO3. These are the common acids in a lab. Hydrochloric acid, sulfuric acid, nitric acid. Now, common bases are sodium hydroxide, commonly known as Drano, drain cleaner. Potassium hydroxide could do the same job. Calcium hydroxide, I put that one in here because these are in the first column. Lithium, sodium, potassium, cesium, rubidium, I can't remember if that's the right order, are all in the first column, the alkali metals, with one outside electron. The next row in, magnesium and calcium, I forget what else is in there, they have two outside electrons. So they can pick up two OH radicals because the OH radical is -1, I guess. Yeah? So these are common bases and these are common acids. Let's get your head around that first. I want you guys to think about the bases. Yeah? How about LiOH? How about Mg? Remember, Mg is in the second column, so I need a 2 there. MgOH twice. These are bases. Let's see what happens in an acid-base reaction. We have an OH and a H. So we get the H coming together. And what do we get? HOH. Hydrogen hydroxide. We call that water, neutral, okay? That's what happens in all neutralization or acid-base reactions. Let's get your head around that. Take it off. We don't need that. I can't remember the acid-base reaction I took down, but we go acid plus base gives a salt again and water. Acid plus base gives salt and water. We'll go again with the same acid. Ah yeah, this is the one I had yesterday. Hydrochloric acid and sodium hydroxide. Let's see what happens. Well, the H and the Na will swap places. And we get table salt again by a different route. And the H and the OH will swap places. Now let's check to see if that equation is balanced. Do we have the same number of constituent atoms on the left-hand side as the right? Let's count. 1, 2. 2 hydrogens. Oh yeah, that's correct. Chlorine. 1, 1. Yes, that's correct. Sodium. 1, 1. That's correct. And oxygen. 1. How about that? It's balanced. Let's try another one. We're going to make it harder this time. Magnesium nitrate. Magnesium is +2. This is -1, so I'm going to need 2 nitrate radicals. Now, once again, the H swaps place with the magnesium. Oh, I did that the wrong way around. Okay, so hydrochloric acid, magnesium. My mistake. We're doing acid plus base. I was giving you the products. So we go, H swaps place with the magnesium. And chlorine, what does that do, I wonder? I guess it's liberated. Magnesium chloride is the salt, I guess. Yeah. Now let's see if this is balanced. Okay. We have 1 hydrogen here and we have 2 here, so we have, oh no, 1, 2. We're missing a hydrogen on the right-hand side. We have 1 chlorine here, and we've got 2 chlorines over here. We've got an extra chlorine on the right-hand side. We have 1 magnesium here and 1 magnesium here, so that's okay. So now what we're going to do is we're going to multiply by some number to even up things a little bit. We're going to multiply this one, this is by trial and error, by 2, and let's see what happens. So now we've got 2 H's here and 2 H's there. That's 4 H's altogether. Well, we need 4 H's on the other side, so we have to go 2 in front of the HOH. By the way, HOH is just water. So 2 waters, 1 magnesium chloride. Let's see about the Mg. 1 magnesium, oh yeah, 1 magnesium. 2 chlorines, 2 chlorines. So it's balanced for the chlorines, it's balanced for the magnesium. 4 H's. 2 plus 2 is 4. And 2 oxygens. 2 times O is 2. So this equation is balanced. We're going to think of a simpler one for you guys and then we'll wrap it up. Acid plus base gives salt and water. Now this is hydrofluoric acid. I can't remember if it's FL or F one way or another. That's good enough for now. Hydrofluoric acid. I should look it up. Okay, good enough. Fluorine is F. Hydrofluoric acid plus calcium. Calcium is in the second column. It's going to be a plus 2 up here. Gibbs. Now we're going to get the fluorine and the calcium coming together. And we're going to get hydrogen given off as before. But remember, the H2 is the formula for hydrogen gas. So 1, 2, it's not balanced. This equation is not balanced for hydrogen. Ca, it is balanced for that, but what about the compound calcium fluoride? Fluorine will accept 2 electrons, so 1 electron. So we'll need 2 fluorine atoms to accept each one of these electrons. So this has got a 2 in here. Let's see if it's balanced for that. No, we're missing an atom on this side. We have 2 there. So what's the cure? Let's try this. 2 H's in front of that. So we get 2H and H2. So that's balanced for the H's. 2 F's and F2. So it's balanced for the fluorines. Calcium, 1 and 1. So it's balanced for that. That equation is balanced. When we're talking about it, we'll say that H2 is hydrogen gas, N2 is nitrogen gas, O2 is oxygen gas. They're all diatomic. Cl2 is chlorine gas. So they exist like that. They don't exist as single atoms. Okay, that's enough for that talk.